All right, good morning, everybody. So last time we talked about tonsillos. This time we're going to pick up, talk about some things related to multiple issue. The next topic we're going to be going into after this is going to be looking at some areas on vector processes and GPUs and that. What I'd kind of ideally like to do on that, a few years ago, I taught a short sequence at my last university, maybe like a 2 or 3 day thing, on how to program GPUs. Now, technically speaking, this is not a programming class, but I think if you understand the programming, it'll help out a bit. And honestly, I think it's useful, and I don't know as engineers how much you hit of that. So my current thought is to try to make that hit into GPU stuff, which means I'd like to kind of pre-prepare that by talking about the hardware issues related to GPUs this time as part of the multiple issue area. So, you know, kind of do some multiple issue stuff, but then do, you know, what's kind of some basics of some GPU architecture and what makes them important and strategic, so that we can then next time go into how do we take advantage of that and program them. So, just give a slight emphasis to where we're going on that anyway. All right, so when we're talking about multiple issue, we've kind of discussed some of the things as they go on through here, but I want to put the initial fine point on it. Everything we've done up till now has been single issue, technically speaking, and we've tried to loosen up some requirements. So, you know, we've noticed that when you did a very strict, statically scheduled, you know, follow the exact order of the programmer and things like that, it was very inefficient. I want to kind of relate a little bit of this to my research because it's a graduate course and I think this is kind of an important thing. There's some work a colleague and I have been doing for probably 8-10 years on this type of stuff. And this relates to entropy in physics. Is everybody familiar with the idea, or entropy of information too, same idea that goes on. If you consider a space of everything that's going on, and you know, if you had, imagine that you had a room that was kind of set up, and you had some little section over here, and all the gas was in there, how likelihood is that? That you just have,
kind of low. Kind of low.
It's pretty low, right? Now, how do you know that that's low? I mean, practically we don't encounter it.
Yeah.
Right?
Yeah.
But why would that be probabilistically that that is low? I mean, isn't every configuration equally likely?
I don't know about that.
Because this becomes important to how do we apply it here. Well, in some sense, let's say I take that presumption, everything's equally likely. And let's just, for simplicity, say I've got, you know, 4 particles. I've got a black particle, maybe I'll just go through, now I can do 4 particles. Well, I need to be able to do 5 particles. How likelihood is that configuration? Same idea, right? All kind of packed together, right? Well, if that's equally likely, but then in order to have it, I'd have to consider all possible configurations, which would include this particle here, right? So if you really considered all possible configurations, I could have ones where they're all out around. Now, if you consider how many spots I could put the particles due to they have a volume constraint on them, right? Because they got a charge field around them, and you can't just pack them in. We're not a black hole here, right? So, I mean, there are limits to where you can place these that go on. If you considered all possible configurations, there's going to be a tiny number of the total thing. So even if you equally weighted them all, the number where they're all packed in really tight together is very, very small, which means you'll get a pretty good representation of what goes on here. This idea was one of the foundational things behind StatMech, statistical mechanics, which is, you know, one of the underlying things that pushes behind quantum mechanics and all kinds of other stuff, and a lot of modern physics is based on this. Well, the idea of this relating to entropy talks about using those same probabilities to be able to talk about how likely some configuration is, and if I wanted all the gases concentrated there, how much work would I have to do to move them in? Does that make sense? Now, that idea, if you consider a volume that they're taking up and how much is there, and considering the probability that you're going to get a configuration that based on permutations, we can do the same exact thing with ours. Consider I just have two independent little threads running. Okay? I've got process 1 and I've got process 2. Now, what we do on most machines as they're going on is we run them, you do one step for each. How likely is that?
It could probably be close, but
that's-
exactly.
But how likely is that to happen if you were to just randomly pick some ordering of commands? Right? If you think about it, you've constrained yourself to ours. You're going to have to go from this corner to this corner, right? Because this is start and that's end for us, right? So you're going to have to go across here. If you consider it, we're forcing you to one path, and that probability is low. Well, what happens if there's a bad configuration of commands along there? What if they're not put in a good order? What if it would have been a little bit faster to have gone around something or slightly reschedule things? And we've seen a lot of these where it made some sense to actually, go over and do some of this stuff, come back and come here, because the data was available. And it may look like a longer path, but it was shorter segments. And you got to think of this kind of like connecting each point. It's like a graph with a weight, how much time between them. And by constraining you to a particular path, you're constraining yourself to a particular cost function down there. That's like saying, I'm going to just tell you in advance an order of some nodes on a graph. You're going to always walk around the outside of the graph. How good is that going to be? Well, maybe it'll be good, maybe it won't. It's how lucky do you feel today, right? This is kind of that whole Google, are you feeling lucky today type of a thing. Well, that's not a good way to do your programming. And we've noticed as we start loosening the restrictions, we start getting paths that start going all over, right? That are going in because they're following whatever is efficient at this moment. Now, if you notice, when we're doing dynamically scheduling, the efficiency they're looking at is local. So now, has everybody had some optimization theory? It's like local optimization and there's global optimization. So global optimization is like I look at the function, I take a derivative, I say it equal to 0, I find what is the optimum, right? Now there could be tons of those that fit within it and you're trying to find the best. Okay? And then there's kind of local optimization, which is like gradient descent. I look at my immediate area and I go, that's downhill. So that must be better. I'm going to walk downhill. If you've got really nice functions, they do the same thing. Do they always do the same thing? No. Does each have advantages? Yeah. Can you always find a global? Yeah, sometimes, what if there's infinitely many minimums and maximums? How do you choose between these, right? What if the solution is degenerate, right? There's all kinds of things that can happen. And there's lots of cases where, what if your function is not differentiable? And there's all kinds of things that can go on to throw you for loops. So both global and local are going to have some restrictions. Overall, global is harder. You can't even guarantee there is a global solution when you're looking at nonlinear differential equations. That's going in. So there's a lot of things that can come up. Well, when we're doing our programming area, hardware controlled stuff, local or global?
Probably local.
Yeah, local, because do you know the entire code?
No.
No, so how do you know what the optimal path is if you don't know everything? Global requires complete knowledge of the entire system. Hardware can't have it. It's got local knowledge, right? How about compiler-based optimization, local or global?
More global?
It is global because it sees the whole thing, but does it actually know all the variables? It's global in the sense of the function, right? The program that you're writing.
If your program is
But you don't know the code.
everything it's running, yeah.
So what you're doing, this is kind of like saying, can you tell me a global solution for nonlinear equations?
Yeah.
Right? Not for a particular one. It's for ones in general. Because your program doesn't have the data. So it's a class of them. So it's global, but for a class not for a specific. So both of them have restraints that there's not enough information to give you a good thing. You can get some stuff off of them. As we start loosening some of the requirements on them, and then on top of it, we add this requirement that everything must move lockstep, right? You must move right down the middle. You must walk on the outside of the graph, right? Well, you make an arbitrary restriction like that, it reduces the ability of your already reduced system to find an optimum. When you consider the entropy of these graphs, walking down that main line gives you a huge problem because you're stuck on the main line. It's as small of an area to optimize across. You can think the entropy is giving you some sense, where are you optimizing on, right? So if you restrict yourself to a small area, you just don't have a lot of room to do with your already limited tool set. Well, the bigger area that I let you go across, it's letting you take advantage of all these different things and let them run in parallel. That means you have more options. Does that mean that the options will necessarily happen? No. I mean, if they're inefficient, don't do them. But if they're efficient, take advantage of them. So the bigger the space you can take up, then the more you have the ability to go in there. It doesn't mean you have to, but it gives you more flexibility to take advantage and optimize and get a better solution. As we have been loosening restrictions, right? Dynamically rescheduling, right? And things of this sort, you're allowing yourself to go into a wider area of the space. And therefore, you're dealing with a system that has more entropy, it's more spread and all the rest of that, but that's good. This is not the only thing that does that. If anybody's into areas on like intelligent systems and stuff of this sort, Bob Marks type classes that's going on. When you look at those, take a look at like swarms and things like that. If they don't spread out and get a high entropy, they cannot actually figure out the space. They optimize based on a high entropy. And a lot of our hardware stuff is actually doing a swarm-based idea that's going in because they're going out there and just looking for where are the efficiencies within them. So we want to carry on these. So if we just plot, what is, one particular process versus another process doing, you add more processes, you've got a bigger volume. But that means proportionally a single line from start to end is going to be taking up a smaller bit of it, right? So I've got a potential to exploit more, but if we make restrictions that don't let me do it, it actually makes the case worse. And in order to handle those, I have to have more control stuff supporting it. So as we start adding multiple issues, multiple things that can get launched simultaneously, there's a chance to exploit stuff, but you of necessity have to loosen the constraints on how things go. And we want to loosen the constraints to just what is required to solve the problem, not what is required by an arbitrary system on ours. So this is kind of my little lead into you on some of where those go. And this is some of our work here, and how can we can take these after the fact and actually discover problems within your program by just looking at the traces. And there will, on a lot of problems you'll see, a typical one that's a performance killer is people put barriers in. You calculate everything, everybody stops, communicates, and goes on. What that does is, where the barrier occurs in the program, nothing can cross there. Where the next barrier occurs, nothing can cross. So you're restricting yourself to this kind of block little areas. So you can see programs that have barriers in them because they put those up. And sometimes people go, hey, I don't have a choice, I gotta wait for the data. And if you have no choice, you have no choice. But if you do have a choice, you can see if I have to put barriers in to communicate, right? I'm not gonna go back up to a previous stage, so you're gonna get this kind of like string of pearls down the main line. And the bigger your space and the larger the program and the more barriers, the tighter in it's gonna constrict you to that main line, which means you're not really gaining a lot from parallelism. There's just not a lot you can move around to optimize off there. So barriers are the devil to us, right? I mean, it's a necessary devil in some cases, but it really does kind of constrain us. So we want to, as much as possible, remove those. Does that kind of make some sense? I'm trying to pull some very, stuff into a high-level area, but there's an important intuition that I think is really often missed on these, of what are we taking advantage of. And every time we're really doing the same thing. If you look at it, everything we've done so far has been loosening in a constraint. Even right down to the data registers. What are reorder buffers? What's allowing you to renumber things so that you can spread things out further, so the further you go. Distributed computing, you're trying to send them out to further nodes, that you're doing calculations further and further away. There are some obvious limitations. Get too far away, speed of light and latency starts kicking in. Right? So it delays when they go. So I obviously can't go infinitely far on spreading it. But the more I can allow things to spread out and distribute the process and not require communication, the more free hand they have in optimizing the speed of my process. So anyway, I just want you to kind of have this as like a framework when we're going into them. All right. Let's consider a simple program that goes on. Let's say I want to add 2 vectors. Fair? So to do this one, I've got vectors, let's say A and B. I want to add them and I want to put them into C. That's going on. Now to do this, I'm going to need to load the address, whatever the contents of A is. Now I'm going to do kind of a pseudo assembly level sequence because I'm not as worried about which particular register. I mean, we can if we want. Do people want particular register numbers for them? No.
We're practicing at virtualizing them.
Okay, this is in register 1 and 2 is the address. That's the start. Right? Memory of that will be the first entry, and so you'll offset. We'll say both of them are size n, and we'll initially stick n into R3. We're going to put ultimately we'll want to store this in R4, and we'll probably throw some temps in just to walk through. So let's say I'm going to first load in the particular value of A, so we'll put the first value of the A1 into R1, and this one into, oops, not into R, that's my address, into R5 and 6. So then we're going to want to add them, and we'll just put that in the final answer, R4, R5, R6, and then we've got to increment our address pointers here, R1, and I. And we'll count down from here, right? So we'll do add I, R3, so let's do 1, that's a straight countdown. And then branch greater than 0 on R3. Fair? For a program. So, we're just loading the first value of A, the first value of B, and I add them together. Oh, I forgot to store them.
It's an optimization.
I know, yeah, it saves you all that trouble of having to actually do something with it.
Yeah.
So I'll just stick a little store word, and, oops, I gotta do that after I add them. Store word. Let's see what's in R4 to 0. Oops.
Top.
I didn't give myself an address for this. And actually, I'll just store this in M. So, okay, I'll just overuse 5. So I'll just store the result because it's a temporary thing. I'll stick it in 5 and then store it to that location for C. Just add them and walk through. Right. So I load the 2, I add their value scarcity into 5, I store it into the memory location, and I increment these, and I should increment that one too. So I increment all my pointers so they go to the next entry. I decrement my counter, and then as long as I haven't run out of stuff, away I go. Right. Notice a couple things. Number 1, first off, I'm doing an add-I, not a subtract. Why?
It's a -1.
Because we have no sub-I.
Oh.
There is no command. Right? And there's no command because I can put negatives here, so it's unnecessary. It would just add extra mud in the space. So there is no such thing as a sub-I command. Branch greater than, or branch greater or equal? I know this always throws everybody. This is off by 1.
Does GTZ mean greater than or equal?
It means greater than 0.
Oh, greater than 0. Okay. That should actually be okay, I think.
It is okay, but why is it okay?
Because
It's actually really easy analysis. Number of entries is n.
yeah.
What did I start at?
You started at n,
At n.
right?
So if you're counting n things, it's 1 to n or 0 to n minus 1.
Right. Yeah.
So if it should have branched on 0, I should have started at n minus 1. Right. But anytime you look at code, this is just a knee-jerk reaction, and I'm mentioning this because this is one of my knee-jerk reactions when you're looking at code. You want to immediately look at things and say, you know, does this make sense? What can I do? What's going on? Now what I'd like us to do with this is kind of a procedure. I'm going to just give these all names. And I want us, just from this code, to say how many commands could run in parallel right from the start, no matter what period.
What about the store word and the other?
Do they need letters?
Oh, yes, they do, thank you, because I completely forgot them. It doesn't, the letters aren't important. A, B, C, D, E, F, G, H, I. Thank you. So how many can I get in parallel on this level?
Well,
Well, let's start with the first, right? Round 1, right? Here's our first time period, right? I'll do 1. A can run. Is there anything that's going to stop A and B?
aside from just memory issues, it seems okay.
The only constraint here is the problem itself. We haven't built hardware,
Right.
right?
Yeah.
So I could give you multiple memory lanes, I could do all kinds of stuff. I could pack those in all kinds of funny ways. I could interleave memory for you. I mean, I'm saying you can do anything, right? Don't put any restriction on this. Because is there any reason I can't store my vectors interleaved in RAM? No, we don't, but is it physically possible? If you could get a ridiculous speed up for something, is it worth considering?
Oh, yeah.
Okay, so we're just trying to say, what can we do, period? What's a limit of this? I can run A, I can run B in parallel, in theory as it goes. Can I run C?
Well, then we want R5 and R6.
Yeah, so you need those to be loaded into the registers.
It needs those, so that even if I launched it, it's not gonna do anything. It has to go at the next time period, doesn't it? It's gonna have to follow. Data dependencies can't be violated, right? You need the information. How about D?
Well, D and E, those look pretty good.
What's the problem from D to anything before?
Well, really just references in the loads, but, you know.
But if they're launching at the same time, doesn't matter.
Yeah, that's what I'm thinking, yeah,
Right?
yeah.
Because these are reads, that's a write.
Uh-huh.
If they launch at the same time, can there be a problem? Because this is a write after read. All right, so the dependency is war.
Yeah.
War,
Yeah.
right?
Well, if we've already stored if we're using like Tomasulas and we've already stored it in an execution station, we should be fine.
Yeah, and so since there is a way, right, remember, I haven't given you any requirements. All I said is, if there is a way, you can do it, because you haven't built your machine yet. Because that's what we're trying to decide. We're trying to see what can we do and then pick something that'll do it.
Yeah.
So I can do it,
Yeah.
which means I can put it right up there. How about E?
I think E can do that too.
Same thing. How about F?
Yeah. Oh, yeah, that's pretty independent, actually, yeah.
That's just the counter, it's the index on there counting down.
Right, yeah.
Okay, how about G?
Well, let's see, we need the condition from.
We need F to go first.
You need F to go first. So at the earliest, G can go here because it's a data dependence. This wrote it, this reads it.
Yeah.
No way to avoid that. What's going on? How about H?
That needs,
Whenever C is done
R.
or loaded on.
Yeah.
Does this change anything by putting H there?
Oh, we
This
haven't
is
done anything,
solid.
we haven't done anything to R5, but it's, we have the branch, I guess.
Why did I do what I just did? It's got to be in the loop still. It's a control hazard. So besides your data, don't forget the control hazard that goes on. I didn't tell you you have a branch delay slot, which will let you carry it after whatever. I just have to specify it's in the loop. So G is now forced to the end, because G has to be in that last group that goes out. Because you may or may not want to go again, so that thing would get lost. It'd get cut out of the loop if I did it. Okay, how about I?
Has to go after C. Well, like.
So you could just go at the top still.
If it goes at the top, right, then it goes before H.
Oh, wait, which one? We're doing I. Oh,
We're doing
okay.
I.
Yeah, okay.
Right. See, I.
Yeah.
Now, if I could have said that as I deliberately did it, it would almost make a reason why I forgot them. It's not true.
Oh, is that R4 in the parentheses?
Yeah.
Okay, I didn't see that. So yeah, okay, yeah, it does have to go after, which means that G also has to move down the line.
What if I told you it doesn't?
I'd say you're probably right.
Thank you. I am, but I'm doing something sneaky. Because remember I told you it has to follow what the program is accomplishing. But remember, somebody wrote this particular down. Did they write the correct commands? Are you trying to run somebody's code, or are you trying to accomplish the algorithm the code is implementing? Have any of you seen like a poem or a song written in another language translated into English? Does it carry the full sense?
Not necessarily.
No, of course not. Then that would be true of an English thing carried into another language. Different language implement things. When you're talking about a poem or whatever, it could be hard tied to the language. But there's also a lot of theory that goes on that it's really an idea you're painting in your mind. Poetry, songs, books, I know this to some people sounds unromantic, but I think it's very romantic in some sense. They're all actually programs running on a human computer. You read a story, it creates a picture in your mind, it creates an emotional state, it creates a state inside a very sophisticated machine, right? Which is why they should let computer science count as foreign language requirement. But, but it really, in a sense, if you think about it, there's actually, you can bring hard analysis to those disciplines by actually bringing in our discipline area looks at them as it goes into it. Well, if you think about all these things as just running on there, it's not the language, right? You have different human languages, you have some styles of programming, poetry, songs, whatever. We have styles of programming that goes on, you know. So we have styles and we have language groups. If you think about them in that way, it's just like happens in regular languages. You go from one to the next, some of them are easier than others. But are we trying to add two vectors, or are we trying to run this exact program?
You're really trying to add two vectors.
I'm trying to add two vectors. So the fact that I put them in this order, what if I switch the order and I put a -4? What if I put I first? It would add 4.
Yeah.
But the -4 right there, it'll knock it right back out. Has it changed anything for the vector?
Yeah, you can get the same result. Yeah.
It's the same exact result, which means it's implementing the same thing. So I can do it as long as I put that caveat, that H and I can not only just move them around, I can actually slightly change the commands to allow me to be able to now resequence things. Okay? Now, we're not asking whether that's practical at runtime or anything else. Maybe it's software compiler, because the compiler could easily do that, couldn't it?
Right.
Right? A static -4, I could technically put those type of things even into a hardware area to recognize it and send the signal to add or subtract 4 if I wanted. So there are ways I could handle this type of thing that's going on for reordering. So that means I can technically move it as long as I allow these two commands to have a little star on them, which means they're kind of coupled together and maybe I have to adjust the constant. But that would allow me to move I all the way up here. Now, adding two vectors together, is that pretty parallel? Just in regular life. In regular life, it's, I mean, if you think about it, there's no order restrictions to a human. I could technically, if I had two vectors of 1,000,000, I had 1,000,000 people, I could give each person one index, and we could just calculate it in an instant. Right? The trouble would be reassembling it, but I mean, conceptually, they're as parallel as you're going to get. We call them ludicrously parallel. What's the level of issuing, multiple issue, that I can achieve out of this? In the best sense.
Well, you get a whole bunch of issues in step 1.
So, you know, I'm getting like 6, and then a bunch of little schmutz. Right? Now, some of this is because there's only 9 commands in there, period, right? So roughly about 2/3 of them in this case I was able to issue. That's, and if you think of it in those terms, that's actually pretty good as a go on. And I'm deliberately picking about as parallel a program as I can think to do. There's no data repull backs. The only thing is memory, and I've loosened that. You can have as wide a memory as you want. So if you think about it in here, I still have some restrictions, even with it, and it's still 3 deep. And I can't get away from that.
Right.
And all I'm doing is addition. So you're not able to get infinite parallelism. And notice at some points I get down to 1 command. So this is our bottleneck that's right there. Technically the bottleneck is the flow that goes through here, the ABC down to wherever my store's H. So this kind of flow here, that's the one that's creating our biggest problem. And our second biggest problem is whatever, F to G. Notice, where are our problems? It's the main data line,
Yeah.
which has the
And-
memory
and
access
control.
on it, and the control loop. Right? It pretty much, that's why even though this one was not because it's memory, but most of the time when you're doing memory, you're accessing data and you're doing it to do calculations that weren't there and the calculations were too big. But we hit that a lot. So pretty much everywhere, you're gonna see that same memory, main data line, and control coming up to be your big kickers. Some of them like this is the core algorithm.
I was gonna say,
Right?
that's the main thing you're doing, yeah.
Okay, this one is the thing that's needed to keep it running, and this is just support. So most of the multiple issue I'm getting is just support stuff. Now the sad thing is we often put restrictions on those support stuff to carry in to just, even cause that to give limitations on our things, and that's really intolerable. That's when our own restrictions have now altered that area. So if you look at it, we've got a maximum length of 3, and we were at what? 4, 7, 8, 9, so we're at 9, right? So we can at most get a speed up of 3. And I'm allowing you infinite size things, right? Issue of 6, speed up of 3, and I'm giving you anything you want. Now, is that totally true?
The speed up or of what you've given us?
The whole thing that I just said, I buried an assumption within there.
Well, we haven't unrolled anything yet, right?
I've made a what we think of as a normal and kind of necessary thing that's not necessary, right?
Which is to keep to the loop, yeah.
To keep to the loop. But I said you don't have to keep to how this is going. This is saying, do one thing and then do the next. So inside one iteration you can go, but we already know we can unroll stuff. We also know that we can actually have multiple things working on. What if I took each one of these and I made a little lightweight processor? I call this little section a loop, right, this little box. But what if I unroll it and just send each of them to a separate little processor? Now, think about how their memory access is going. If these memory accesses are going all over RAM, you're going to have a problem, right? I mean, infinite universe and everything, you could get some stuff, but there's still going to be some limitations here on where it goes in. Is there anything that helps me out with the memory access portion of this by kind of unrolling and putting little chunks of the program out to the side?
Well, there's no contention. They're not going to the
Why?
same places. Well,
Okay, so there's no contention, so that's a good thing. So it's
Right.
not like we're trying to have two things right to the same spot. But what if one was going to the beginning of memory and some other one was going to some spot in the middle and
Yeah.
some was going to the
Yeah,
end?
that'd be
It gets
wrong.
really hard to just kind of grab. If they were truly random across the entire space, you're gonna run into cache muck problems, right? Now, again, I didn't say you have to have cache. You could try to design some new systems, but you start running into a problem. When you just open it up and say access anywhere at any time instantly, you run into a problem called p-space. Okay, which is there enough memory period? How does the space grow as complexity of the problem? As that vector grows, you start running into difficulties accessing it. As memory or time, which is a worse constraint if you let them go to infinity?
time. Wait, we let it go to infinity.
Yeah, I'm letting each one go. Requirements for time, requirements for space going to infinity. Which one is the worst one to deal with? How many go for time?
I want to go for time because it never gets done.
Okay. Do we like that? Yeah.
See,
I want you to actually think and have a reason why. Because
Well,
there is an
I
underlying
want to vote for
problem.
both is my problem, really.
I know, because nobody wants
Well,
to.
because the problem with space is that if you can't, like you were saying, you can't really load in all of your RAM when you want to, if you have things all across.
Well,
But
yeah.
and it depends
So,
on what do you mean by infinity in time. If you just mean that it takes a few
The
extra.
problem grows unbounded.
Okay. Yeah, then.
Which is worse, time or space?
Well, see, I feel like we could build a finite amount of space, but we can't build an infinite memory. And it's like we could let it try to run forever, but we have to sit here and wait, and we'd get really bored. But we could build a finite memory if it's just gonna take forever to run. So we could build it, but it would never finish. Versus, maybe we could build the finite memory and then it never finishes. Or I guess the other one is,
Just
we
takes
can't
longer.
actually build the infinite memory. So that's our problem. We can't build the infinite memory.
Yeah.
So
Memory
which
is
problem
worse.
do you want to choose?
P-space is worse.
Okay, yeah.
P-space is worse. And it's actually, you can show in complexity theory, it is worse. So the P versus NP problem that everybody always hears about is a smaller, simpler problem than P space. Okay? To give you some perspective on it, how big, and it actually hits earlier than you would think. If you took the entire known universe, 38 billion light years across, you packed it solid with electrons, okay? Right, so an electron's what, about 10 to the, put it simple, say like 10 to the minus 12 meter or something like that. That's going on. We want to cube it. That's going in. So we'll have 10 to the 12th of them. It's 10 to the 12th cubed inside that meter, right? And, meter going up to, from here to the sun, we got what, 93 million miles, which is, roughly double. It's called 100. So say, 200 million kilometers, somewhere in that ballpark range, right? Let's just round that up to 10, right? I don't care, the big numbers ain't gonna kill me at all. So, 10 million, we're talking 10 to the 10th, somewhere around there, or sorry, 10 to the 7th that's going on. So I've got, no, writing that. So, and we want that cubed, so that's the volume around. That gets you about, 1 astronomical unit out that's going on. And, we're gonna take those ones out, well, actually I can do this faster, that's meters. Let's just go light years, right? Light year, that goes on, light travels, what is it?
It's like 8 to 12 minutes from the sun, I think.
Yeah, I thought it was a little good. I thought it was like 6 minutes.
It
one
could
way,
be.
12 minutes round trip. But,
Could be.
we got 3 times 10 to the 8th, so we'll just call it 10 to the 9th. That'll get us a light second that's going on. So that's a cubic light second, right? Say there's 10,000 seconds in an hour. Well, that's 3,600, but again, just working them out. Every time I'm going to round up, so I make our universe bigger.
It's a
This is,
different planet. Yeah.
But when you take it in, you get 10,000 in a second, and then you got 100, just round it up, 100 hours in a day, right? It doesn't add up that fast on the exponents, if you notice, when it's going in, right? So, and then we'll say another 10 to the 4th or 10 to the 3rd in a year, because that's 1,000 rounded up from 365. Every time I'm rounding up, much bigger, 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 that goes on. So that's light years, and then we've got what, called 100 billion, right? So 10 to the 11th. So I just add my exponents, 20, right? 25, 29, 39, 41 cubed. So it's 10 to the 120x. And that's an oversized universe with extra long, just everything much, much longer that's going on. So let's just, for safety, let's go up to 150. Let's go in. Because now I'm like way ridiculous beyond this whole thing, right? That's packed solid with electrons. Right? I'm going to use every electron as a memory storage device. How much memory can you store?
That much.
Okay.
Yeah.
There you go. So, now when you're looking at this, if I want all the possible states of, for instance, a genome, I want to store them. Well, genomes can store, technically, in our case, it's 4 to the x, it goes on. But that's 2 to the 2, right, to whatever else. Now we know 10 to the 3rd is about 2 to the 10th. This is actually a little bigger. So I'm underrepresenting this that's going on. So that's 15, right? So if I broke this in, this would be 50 of these units. This is 50 times 3. Right? So if I take this is, right, 50 times 10 to the 3, right? That's this, 10 to the 150. That means that it's 2 to the 10th, 10 to the 3rd, right? Again, following my rounding up.
2 to 500. Yeah.
So 2 to the 500 gives you a nice little overbound, but I can't actually use all those. I got base 4, so that means I go, that's every possible DNA string up to 250 in length. How long's your genome?
Pretty long.
Billions. So if I wanted to check every possible genetic string out there to see what is possible for life, for instance, or where could a genetic disorder be, or whatever else, could you do it? If you had the entire universe.
That's memory, man.
Wow.
Right? Do you realize, I mean, this is why when people talk about I can exhaustively solve problems, it's laughably stupid, okay? So I want you to think, when we get to the memory situation, and I say, hey, we just throw memory on it, you should always ask yourself the question, reasonable, unreasonable. This is why when people make claims, oh, I just search through all this stuff. No, right? There are things, I mean, if you realize that there just isn't enough space in the universe to do this. So the optimization routine to try to figure out what's good genetic code has to be really awesome. This is why there's real serious science behind bioinformatics. Because if you're trying to search that space, right? It's A, rare, and B, you just cannot do it the dumb way. People just go, well, I'll just exhaustively search it. No, you know, not possible. And if you consider the random just generates out there, now you've got random accesses into a thing you couldn't store in the universe at a density of a black hole. I mean, it's just so amazingly crazy, because realize the density of this is solid packed. It's incredible. So there are problems that won't do this. This one will. Why? Because the way your memory is already organized. The problem, you're grabbing vectors. It's a nice problem. It's not that problem, right? There are ugly problems and there are nice problems. And what you want to do, and part of why I'm bringing this up, and this is where a lot of the intelligence programs and everything else get into, there are easy problems and there are hard problems. And when you look from the outside and you don't know anything, you have no idea to distinguish an easy problem from a hard problem, which means when your boss or your job or whatever comes up and says, hey, we want to solve this, there are some problems that are easy that look very similar, human worded, to problems that are just darn impossible. So you can easily make completely dumb statements, right? You want to get used to the idea of being able to think, scope, and pull. This one works nice because the memory for all of your vectors are linear, they're nice and connected together, and you're treating all of them completely independently. Right? Your vectors that you're processing are scoped within our normal area, so it's not going to grow big. So it's not like I'm looking at every possible, you're not adding up every single vector of length n. You're adding up two particular cases. How much space does it take me to store two particular, right, genetic sequences of 250? So tiny I can't see with my eye, right? So when I go from the difference between all to a finite subset, it's a very different problem. And this one, it's all nice and linear. When I go to cut these up, the memory sequences, if I put, you know, entry 0, entry 1, entry 2, entry 3, if you were to just go and access the first thing, you'll grab the whole sequence of them inside your cache block. Memory's already designed to handle that. I could increase the block size to handle larger ones, so I can make your memory really wide and just load in a gigantic chunk. I'm not saying we'll necessarily do it, but I could, in theory, do those type of things. It's not hard, and a lot of machines do. It's just how big do you make it, right? So the idea of splitting this up and separating them is already within our current hardware. So your memory restrictions of what's the latency to get the data is going to be drastically reduced by just cutting them. Now, if I just randomly pick things out of there, I'm going to be in deep trouble. But if you pick them in an intelligent fashion so you follow the way they're grouped and ordered inside the sequence, the memory problem will go away. If there is a way to make the problem go away, I'm allowed to do it. Right? That was our idea. So by separating these out, I can make them parallel. Could I do 4? 8, 16, 32, right? How far could I take that? I could take it pretty far in theory. In
Some of us in
practice,
that universe thing, yeah.
so now we've got a whole bunch of these individual little thread chunks running, doing stuff. And the next group, how's it gonna look compared to the code? The code will be the same, right? Because I'm gonna take this, and let's say I chunked up your vector addition in. You know, you're gonna have a different set of memory, but you're gonna have the same exact program running. You know, whatever, let's say I did, you know. So do I need to reload the code?
Not if it's done right.
Chunk, chunk,
Yeah.
chunk, chunk.
Yeah.
No, I just say, you know, I'm gonna make you, in here, there's kind of like we see there's a stream, there's a data stream. So inside here, each of these, there's a data stream. Why do I need to reload that stream? I can take a window, and we've already talked about these for instruction buffers. I take a window, I get it ordered well so it's nice and efficient, and then, right? And I don't need to reload anything, I just need to get the data. So your memory accesses just went down. Your data limited, right? That's, I mean, the only memory problem you have here is data, but as long as I do really crazy wide data on this, I'm good. But this required me being ludicrously parallel, like vectors. So anything we can put in this type of a format, and just chunk, 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 right, with little streams in here, we're gonna call it a vector processor, because it's really good for processing vectors. And we can call these little things here, that are handling an individual stream that it's gonna keep repeating, we can call it a stream processor. Well, welcome to a GPU. This is how GPUs are set up. Little tiny, we call them stream processors. We group them into groups. The standard one is a warp of 32. Right? This kind of looks like, if you think of each one of these as like threads, everybody see a Jacquard looms? Right? That's the original kind of programming thing, an automated one for weaving fabric. Right? It's a whole bunch of strings going in parallel. A group of those strings going in parallel on a Jacquard loom is called a warp. So when you look at fabric, the direction going down is called the warps, and when you're cross-cutting, it's called the waft. So there was this old thing, the warp and waft of it, right? Saying kind of the whole dimensions of the problem. Not like I want to teach you tailoring, but that language has exactly come across. So a group of these is called a warp, because it's a string coming down. When you're doing with one, it's a waft. Right? So, and that's, if you wonder where the heck did they get those things, like some people think it's like a Star Trek reference or something, you know, you're going warp speed. It's not, it's a reference back to the Jacquard looms. So, but we would take each of these and do them. Now, going from one to the next, I need to do that very quickly. It's going in, but it's already loaded, so I can't. So I want a very small, lightweight control system that'll just quickly flip them back. If it's complicated, it will take too long. Right? So the key thing is to have the switch between these go really quickly. And once I'm done calculating the vector and I need to pull the next thing in, it needs to flip in with very little delay here. Right? Now, there's always something between when I'm going to go from here to where I'm going to go here. There's got to be some amount of delay, right? So would you be surprised if I said the NVIDIA stuff is context delay 0? The context switch from this to this is 0. How on earth does that happen if there's always a delay? Because there's a setup for this whole thing, right?
Maybe you're loading this, maybe you load like the setup while the other one is in the middle of executing.
You've got all your streams here. I've got all the setup for this on this one. I do the setup for the next one, and it's all ready to go on the other. And then all I have to do is switch, so I can be preloading. This is just a standard buffering scheme. This one's running, I'm setting this one up. Once this one's done, all you have to do is switch that. Right? And you've reattached your very fast streams to a reasonable chunk of memory as it goes in. So now I can switch very quickly. It means you can now use it very efficiently as long as you can pull memory in. This is why there's such a big deal on all the vector processors to have crazy amounts of memory bandwidth coming into the system, because what's my one big limiter? Yeah, starving on your data. That is your big physical limiter in a very open system like that. or if you have an algorithm that's not a vector. That makes some sense? Where it's going on? This is where we said, hey, let's loosen it up. We picked a problem. We look, hey, we can take advantage of that problem. We can get a crazy amount of parallelism. We can get a good amount inside here at IOP stuff, but there's obviously limits. 6 for a small thing, pretty much 8 to 20 is about reasonable for a typical code. There are some really specialized codes that have these gigantic loops that they've unrolled a bunch that you can get up to 30, 40. Some people with real special ones have gotten, somewhere to the high 50s. But it really, they're rare and far between, so I wouldn't count on getting anything out of that type of area. Most people look at it, it's about 8 to 12 is good numbers. For a parallel, for a really nice loop, you're just stuck. Multiple issue can only go so far. You've got to start getting into threads in order to take advantage of the other areas of the loop that's going in. And therefore, there has to be a structure between them, because notice, GCD test could kill me, right? That's going on. In this case, it doesn't, because they're all completely independent.
Well, if you're only looking at running like 8 to 12 processes at once, I mean, the CPUs these days now have, quadr, like either 4 or 8 cores, each can run 2 different threads themselves,
So on this one, but remember, this is instruction level. I can get about 8 to 12 issues, and this is in the CPU. So each of those cores could get up to 8 to 12. Over here, I can, a group of 32 that goes in. Modern ones of these are, 2,000 to 3,000 in parallel.
Okay. Then that opposite makes more sense.
Yeah.
Is there a lot more?
Because I can just but the reason why they group them into blocks of 32 is because that way you can have one group of 32 working on one problem and another one working on another. Right? We call that one simultaneous multi-threading. There's coarse and fine grain and all the way up to simultaneous. It's how fine can you break these apart, right? So we try to define our problem so that, there's a chunk here and I can be loading a different problem into another section of this to get working on. And it's got one section doing its thing and another section can be working on a different problem and another on a different. And then you're trying to restrict your number of switches. But the finer the switches, the better we can widen down into that whole entropy space to take advantage of the optimization, so the better it can go. So we keep trying to push the finer and finer grains on how to pull them up. But right now, blocks of 32 is pretty efficient, so that's how people try to organize them. But it's, usually somewhere up around, 2 to the 11th, 2 to the 12th, somewhere there is the number of streams. So, yeah, good question. Okay, do we feel good? We got to, at least on the hardware and why it's all there and why we're doing it. So the next time we'll talk about how to program these beasts.